Welcome to this talk. I'm just who I am. My name is, hold on, let me just make sure it's working. Okay, cool. Yeah, so my name is Hannah Howard. I'm the primary author of the GraphSync protocol. You can find me on the internet at TechGirlWonder. I use she, her pronouns. I work for an organization called Carbon 5. Carbon 5's product development agency. We've been involved in the development of Filecoin since almost the very beginning. We're one of the sort of like longtime partners with Protocol Labs. And I've been working on IPFS, GraphSync, Filecoin for over a couple of years now. This talk is going to be super improv a little bit. I put this together right before, it was sort of last minute, so bear with me. We're going to do our best. Let's dive in. Cool. Okay. Let's talk about GraphSync. So GraphSync is a protocol to synchronize Merkel DAG graphs across peers, which probably means very little to anyone who doesn't know the deep technical innards. So let's find a different definition for GraphSync. I would say GraphSync is the thing that gets your data from one place to another in Filecoin. Everyone understands that. So I'm going to go with that as my working definition, and then I'll talk to you about how it actually works and where that other definition comes from. Cool. So let's talk about the Filecoin environment and how data transfer and how we need to move data around in Filecoin. The Filecoin environment has some pretty interesting characteristics. One is that essentially no one, I'm calling them peers, but no one involved in Filecoin trusts each other, right? Anyone who can participate in the Filecoin network is potentially someone who is a malicious actor. For the most part, people are untrusted. That means that when I receive a request for data, unless we have some other mechanism for verifying, we don't trust that the person who's making the request is actually acting in good faith. They may be trying to request lots of data for the purpose of just slowing my computer down and or basically causing me to run out of memory. Also, if I am requesting data, what I get back by default, I can't trust. I have no way of knowing whether the data that I am getting back is the right data, unless I have some way to verify that, unless I have some way to prove that it's the correct data that doesn't rely on trust, I cannot trust it. So, so our goal is that we want to be able to do these data transfers in a way that minimizes the effects of malicious behavior. A key aspect of that is that our transfer, as we transfer data from one place to another, we need to be able to verify that data, and we need to be able to verify it incrementally. So we want to know that we're getting the right data, and we want to be able to know at every step of the process. So if we're transferring gigabytes of data, we need to be able to know that at 1 gigabyte, we've already gotten the correct first gigabyte, and then the correct second, the correct third, so that we don't get all the way to the end and find out it was all just garbage. The other thing is that we would like for this transfer, despite these properties, to be fast, ideally as fast as a transfer over traditional HTTP, or faster, ideally, in some cases, though in the case of Filecoin, we're usually just moving from one peer to another. So it's essentially pretty similar to an HTTP setup. One thing that's going to be key for that is we would like to not gate that transfer around round trips between the client and between the requester and the responder. We want the responder to be able to send data without waiting for the client to acknowledge that they verified the correct data. So what is that? So what is it that we're transferring here? So basically, the key to doing incremental data transfer is to transfer it with data structure we call Merkel DAG. Now, these data structures, Merkel DAG is a really common data structure in all of sort of protocols, protocol software. You may, if you've used IPFS, you have probably worked with Merkel DAGs. What a Merkel DAG is let's say I have a giant chunk of data, right? Now, I could arguably take that entire data, hash it, and then basically say, send me all of the data and verify that the hash that I get matches the hash you told me would be the data would have. And that's a simple way of doing it. But if we wanted to break up lots and lots of data, a Merkel DAG is essentially a series of blocks of data, each of which have a hash, where the root block has links to additional blocks. And those links are the hash of those blocks. So you can imagine in this diagram, you have a root block and it has some sort of hash. I'm putting these like QM hashes because those are usually the what hashes often look like in IPFS and Filecoin. We refer to these as CIDs, or content identifiers. They are essentially a mathematical hash plus some additional data. And you would imagine this root block, you can see somewhere inside the data for the block, we have the hashes of the blocks that it links to. So here you have a link to this block, and here you have a link to this block, and they each have their hash, and then they have links to other blocks, right? So this is essentially a way of breaking up a giant piece of data into smaller bits of data, where at any given level we can verify that we have the right data and we know how to get the next bit of the right data. So that's a Merkel DAG. What does the actual inside of these blocks look like? It could look like anything technically, but the actual structure that we use for Filecoin is something called IPLD, which is essentially a distributed data format. There's a talk, I think, on the main track later today where you can learn a lot more about IPLD, but essentially it is a format for distributed data. The short form, you can imagine that what it looks like inside of a single block is you might have a series of nodes inside of a block where each node is a type of data, right? You might have an array node, which is a set of an array of other nodes. You might have a map node, which is like, analogous to a map or hash table or just like a JavaScript object. And then you could have individual data nodes. You might have an integer node or a string node. And then you might have a special node type, which is a link node. And a link node is essentially a link to another block of data. So the short form that I use for describing IPLD is distributed JSON, which is a super simplification of what it actually is, because IPLD, one of its explicit goals is to not be tied to a serialization format. It can be serialized as JSON. It can be serialized as something like CBOR, which is the common binary object representation. We also use protobufs for it. But it's very easy for me as a human to think about it, or a human programmer to think about it as JSON with links in it. So you can imagine this is a JSON representation of what I showed you in the past diagram. And so here it's basically, it looks like JSON, but we have this one special type, which is this link type, where we actually have a link to another block. And with that addition, we can essentially build a distributed data structure. So essentially our challenge is, how do we replicate a Merkel DAG of IPLD data over the network, right? Now, you can imagine if we were doing traditional HTTP, we could probably throw out all these data structures, and we could throw out the need to verify incrementally, and we could rely on essentially like an SSL certificate as a way of verifying authenticity, or essentially we could trust that, as long as we can verify that the SSL certificate, for CNN.com is valid, and we trust CNN for whatever reason, we can trust that the data they're sending is correct, and we can simply send all the data across and then display it. We probably don't even verify it. And often, when you're downloading files from the internet, unless it's a security conscious site, they won't even give you a cryptographic hash of what the data you're downloading is, so that you can verify it. You just download a program and open it, which seems extremely, extremely risky. But in any case, that's essentially what you're doing in HTTP. So we've developed ways over the course of the development of IPS to transfer this kind of data in a trustless environment. And the original solution we have is this protocol called Bitswap. Bitswap is essentially, the basic way it works is you request a single block from another peer. You request one block starting at the root. And you say, I want the block with this cryptographic hash. And then when somebody sends you back that block, you can look at that block, run a hash against it, and verify that the hashes match. You now know that that block is valid, and therefore the hashes to other blocks inside that block are the hashes to the remaining data. So you can imagine we would make a request for a top block or for the root block. And then once we've done that, we could traverse down to one of the links in the block and request that block. When we get the data back, we can verify it again. And then once we get that back, we'll know the links to the next child blocks, and we could essentially proceed that way, block by block, all the way to the end of until we've got an entire graph of data. Now, this is the challenge with this is, in order for me to request any blocks after root, I have to get the first block. And then in order to request any blocks after that, I have to get the next block. So you have a whole series of round trips that happen where I can't request parts of the data until I have some of the initial bits of data. So that's a potential big speed slowdown. Now, we have some ways of speeding that up because Bitswap is very parallelized. So what we can do is, once we get the first block, we can make the next two, request the next blocks from two different peers at the same time. We can do all this stuff to massively parallelize it. And if we have a data structure that's like a tree structure for our DAG, this actually works relatively well, because as long as the tree is wide and not too deep, we're going to actually be able to utilize the parallelized requests really well and get that data back quickly. Now, the downside is if we had a structure that's very deep and very narrow. The actual most extreme example of this is something like a blockchain, where each block only points to one parent block. And in order to get them, you would have to do essentially n round trips for n blocks. It's very not ideal. So essentially, so what we need is a way to express what we want from a block and its child blocks that doesn't require us to know the hash of every single block in the tree, right? What I want to be able to tell a person that I'm requesting data from, I want to say, I want this block and I want all the children underneath it, and I want all their children's children, and I want all their children's children, right? Or I might say, I want to request this block and I want only the first child or I want the child link that has this name, and then from that I want the child link that has this name and this name and this name. You can imagine if a Merkel DAG represented a directory tree, we might request it in such a way where we were essentially, each link was a subdirectory all the way down to a root node. So we have a language for expressing this kind of a query, and it's called an IPLD selector. This is sort of just a diagram. There's a whole series of different selectors you can do in IPLD, but the short version is it's a query language for Merkel DAG graphs. It's a way of expressing a query against a Merkel DAG graph that based on the Merkel DAG will return a predictable result. It's somewhat, you could argue it's analogous to either SQL or GraphQL. It's a way of like going against unknown data and getting a predictable result. So given all that, let's revisit our statement. So GraphSync is a protocol to synchronize graphs across periods. And what GraphSync allows me to do is it allows me to send a root hash to another peer for a graph that I'm interested in, and to send with it a selector which expresses all or part of the subgraph below that root that I am interested in, and then to have the other peer send me all that data back. One thing, so I think the easiest way to think of GraphSync is it is essentially an IPLD selector traversal. It's like running a query against, if we think of like the Merkel DAG as like its own like database, we're running a query against a Merkel DAG database, but that database lives on another peer against a networked data store, right? So I always say that GraphSync is an IPLD selector traversal backed by a network data store. So that was a lot. Just a couple other constraints to know about GraphSync. GraphSync was originally developed for IPFS and then has been moved into Filecoin, and actually seen most of its development in Filecoin. But because it also is intended to work in IPFS, we have to work with like some additional constraints. In addition to peers not trusted and requesters not trusted, any peer on the network is a requester and a responder. It's not like a client server environment. Anyone can serve GraphSync requests. Anyone can receive GraphSync requests. We may have to serve multiple requests at once. So we're trying to optimize, we're trying to build an implementation that optimizes for handling multiple requests. Oh, sorry, I apologize. I'm trying to think if there's anything else. Basically, just that, you know, it is a generalized protocol for moving this stuff around. So it can operate in, it's intended to operate in all kinds of environments. And so we have all the concerns that would come from IPFS, DDoS, you know, making sure that we balance requests between peers, all those types of things. And those are all concerns that are implementation level concerns as opposed to protocol level concerns, but at least the Go implementation takes into account all of these things. Cool. Wow, that was like a mouthful. So I want to look at the GraphSync protocol first, and then look at a little bit of the architecture of GraphSync, and then look at a little bit of the Filecoin specific questions. But I want to, just before that, I just want to make sure, I don't know, how do I get to, I don't know if we have any questions. I can't, for some reason, I can't see the Q&A. So, oh no, there is no Q&A for this. Oh wait, here we go. We have a, let's see, chat. Sorry, not yet. No questions yet. Oh, wow. This is all 100% totally comprehensible to all of you. I love that because you're all geniuses, because I don't understand any of it. Anyway, so let's go into, let's look at the GraphSync protocol. So that's going to be kind of the end of my slide deck. So I'm going to just be showing you some bits from code. And other sort of like online documents going forward. So let's look at, I want to just look briefly at the GraphSync protocol itself. This is the IPLD specs repo. This is where you will find the specification for GraphSync. Here we go. Let's see. Let's look at this. Okay, I'm going to skip all these and just get to the protocol. GraphSync is currently a protobuf-based protocol, which is probably going to change at some time in the near future. We're trying to move things to CBOR, but for the moment, it's a protobuf. On the GraphSync protocol, essentially it is a libp2p protocol. Two peers connect over libp2p and then connect on the sort of like GraphSync, and set up a stream that's set up for the GraphSync protocol. And they send messages back and forth that look like this. A message contains, I have a question about selectors. Okay, cool. So a GraphSync message contains these fields. It contains a set of requests, it contains a set of responses, and it contains a set of blocks. Importantly, each message can contain multiple requests, multiple responses, and blocks that are tied to one or more responses. This bool complete request list makes me anxious because this is no longer super well used. So I'm just looking at this and seeing things where I'm like, oh, wow, we should probably remove that. In any case, so you have requests, responses, and data. A request consists of a request ID, a root is a CID, a selector is an IPLD selector. It's encoded as CBOR bytes in the context of GraphSync. The requests have priority, and then there's two special types of requests. There's a cancel request, which means what you might think, and an update request, which is a way of expressing essentially some kind of update to the existing request. Importantly, both the request and the response have a set of extensions potential that that may or may not be present on the request. And this is really important because GraphSync is designed to be an extensible protocol, and we use this extensively in Filecoin, essentially as a way to, you can layer on side protocols into the GraphSync request process. And this allows you to do a lot of really cool stuff. Like, it's almost like you can think of these as like being either your SSL extensions, maybe like your TLS extensions, maybe even like cookies. It's a way to, like, you can do authentication with this. You can do, you can essentially, you know, in retrieval, we exchange payments through these extensions. It's pretty cool. A response is really simple. A response has the request ID of what it's responding to, and it has a status. Now, there is one extension that is in the response, which is mandatory, that needs to move out of the extension. It's still currently technically an extension, but it is included in every working GraphSync request, and we most likely will not be able to process requests without it. Sorry, that's a side effect of the process of building it. And then you essentially have a series of blocks. Blocks are essentially a CID prefix and then the data. You verify these blocks by essentially taking the data and hashing them so that you only get the CID of these blocks from the data itself. You don't want to transmit that independently, or you would need to check it to verify that the blocks are in fact what they are. So this just allows us to construct the correct CID from the blocks. That's what this prefix does. And that's basically the whole of it. One key other element in the protocol is, I'm going to go, sorry about this. I'm gonna go back here. How much time do I have? 7 minutes. Wow, this is going quick. One key element in the protocol, this is that must-have extension that I mentioned, unfortunately, which is this response metadata, which will be encoded in the response. And it will essentially say, for this response to this request ID, here are the links that I have traversed. And it will tell you, and with that, it will include two additional things. It will include one additional thing. One is, and it's essentially whether or not I had the block in this traversal. One scenario that can definitely happen is I can express a selector to a remote peer. They can start at the root and start performing the query and find that they are missing one of the blocks in the process of the query. This is particularly an issue in the IPFS environment. In the Filecoin environment, generally, you're the one for like storing. You're the one who's like storing the data that you want to store, and so you tend to have all of it. But in any case, it's important, particularly for security reasons. So that is essentially the protocol. Now, the key thing that we need to, so I'm going to talk a little bit briefly about the architecture. I'm going to move over to the Go GraphSync repository. Something, here we go. These documents in the, this is the Go GraphSync repository. It does have a document folder, and it has an architecture document. Some of this architecture is a little out of date. I need to update it, which I will in the near future. But the basics are pretty, I don't know, accurate. And the key thing to understand, so Go GraphSync has top level interface and a requester implementation, a responder implementation, and a message layer for sending messages. In order for us to do a round trip request, a requester needs to essentially encode and send the request to the responder. The responder needs to receive the request and perform an IPLD selector query based off of it. The responder needs to load those blocks as they're performing the selector query, load the blocks from local storage, and then it needs to encode and send blocks traversed and metadata about the traversal to the requester. Now, here's the key step. Requesters need to verify blocks received are the right ones for the selector query requested. So because on the requester side, we do not start with all of the CIDs, and we're not doing the sort of Bitswap bit-by-bit verification. On the requester side, we also run a selector query on the incoming data to verify that it is the right data. So we know the root on the requester side, so we can start with that root and perform a selector query as data comes in. against it to verify that it is the correct data. And it's importantly, we do not save data that is not that does not match the selector query. Once we do verify it, we need to store those blocks, and then we need to return the nodes to the caller. So those are essentially, that's like the overall sequence of events. And again, I'm like putting all this commentary in here about how I think of a GraphSync request as an IPLD selector query that happens locally, that happens to be backed by a data store that's on the network. Okay. This gives you like, I'm probably going to not go too deep into the architecture here. Essentially, this gives you like all of the step-by-step of like what's going on. Importantly, we want to make sure that as we're processing multiple incoming requests and sending and also responding to requests, making outgoing requests, that we have a mechanism that we essentially balance our workloads so that we don't get overwhelmed. And oh my goodness, it's 12:27. So I'm going to probably wrap this up so that we can get a couple questions in before the end. I just want to talk about one other feature, just so you know, before we do a Q&A, which is that GraphSync, the Go GraphSync implementation has a number of additional hooks that are used for you to hook in with extensions so that you can perform additional computation on incoming requests. For example, we have like an incoming request hook. Sorry, this is the wrong thing. We have an incoming request hook, which allows you to look at an incoming request and accept or reject them based off of additional information in the extensions. We have an outgoing block hook, which allows you to like pause requests as blocks go out. We have we have essentially hooks for everything. So with all that, you can build lots and lots of protocols on top of that. And that's what we do for data transfer in both storage and retrieval in Filecoin. Anyway, I have 2 minutes. I'm going to go with Adin's question. I have a question about selector and implementation level details. I'll figure out a way. Yes, go for it, Adin. Unmute yourself. I'm going to stop screen sharing.
Okay. Basically, I wanted to get a better understanding of like what types of selectors we have or we can use, and how we can then use those to then create like multi-user queries, right? So we can start using GraphSync to query multiple peers for data.
Sure. Yeah. So to be clear, we generally do not use the Go GraphSync implementation for multi-peer queries at the moment, because in Filecoin, we're primarily transferring data from one person to another. However, that is an intended goal of the software. And the facilities we have, the sort of selectors that we have right now, we have let me see if I can. We have field selectors. We have array selectors, meaning I want these elements of an array. I want these named fields of a map. We have recursive selectors, which are really key, which is essentially I want you to perform the selection, then I want you to keep doing it again until a condition is met. And that is used for stuff like doing a whole DAG traversal, meaning like I want you to, at each level, I want you to explore all the fields and then traverse all the fields. And then I want you to do it again until you get to, a certain depth. Now, there are certain selectors that we have, which are, there's certain things that we might use, like we could use a field index. So to do some really primitive request splitting, like I want, you to give me the first field and all the children under it, and you to give me the second field and all the children under it. That's not going to be very good for balancing. To balance, we're going to probably have to do some updating of requests in the middle, because we don't really know the shape of the graph ahead of time. The other question that's a little complicated is figuring out how to split up, whether we want to split up a request at the selector level or the block level. Because GraphSync works with blocks, we could easily build an extension that says, I want you to, count blocks by 5 and only send me, the ones where the block count mods by 1. And then like to the next person and give me a block count that mods by 2 and mods by 3, and essentially make the same selector query to all the peers, but they each send back different blocks, and then you verify it. Obviously, that has its own problems, because if one peer is not sending you the right data, that breaks it for everyone. There's a number of different things that we could do. There is also, I think I mentioned, an update request in GraphSync now. So you could, in the middle of a query, change the query and say, hey, listen, I don't need you to send me this part of it, those types of things. That stuff is all a little bit of a frontier that's probably one of the next main areas for development in GraphSync.